Good morning, good afternoon, and good evening, everyone, depending on your time zone. My name is Lucia Chaltema, and I will be this session's host. Our speaker today is Christopher Ariza, talking about why datetimes need units to avoid the year 2262 problem that we're going to have, or our great grandkids are going to have. Christopher Ariza is CTO at Research Affiliates, focused on investment strategies and research. His background is slightly different. He comes from the music area. He got a degree in music at MIT and did some more research in that area. So I'm really curious how his path was from music to going straight deep into Python programming with Datetimes, which is an area I'd rather not work in because it sometimes can be quite tricky to deal with that. So please take it away.
Great, thank you for the introduction. So as covered in the title, what we're going to talk about today is datetime formats, in particular the NumPy datetime64 format. So I have three motivations for talking about this with you all today. The first is there's a lot of confusion out there about the various datetime formats that exist. We have the NumPy datetime64 and we have the Python datetime, and there's a lot of confusion about those. What is the difference between those two formats? We also have some other things around like the Pandas timestamp object, which also can lead to some confusion. The second motivation is in many years of working with pandas, I discovered some curious behaviors. For example, nanoseconds would appear everywhere without me understanding why those nanoseconds were there. Furthermore, I would find my colleagues using maximum dates of 2262 in various places, and that seemed very strange. Third, for many years now, I've been involved in creating an alternative to Pandas called StaticFrame, an alternative data frame library that enforces immutable data. And in approaching the implementation of this, I took a different approach to implementing index objects and supporting datetime64 arrays with units. And that also sort of motivated me wanting to share my work in that area in this presentation. So my title references a year 2262 problem, which is not going to happen anytime soon, but is a useful case for us to look at. So some of you will remember the year 2K problem. This was the issue where systems around the world were using two characters to represent dates, and the fear was that 1999 would advance to 1900. Well, the Y2262 problem is kind of similar. What will happen is a date at April 11th, 2262, if advanced one more day beyond that, will overflow or raise an exception. So this is not obviously an immediate danger, but the Y2262 problem illustrates a data type misuse in pandas, and it's caused by the exclusive use of nanoseconds for all datetime64 representations. Now, it doesn't have to be this way. We can use appropriate units with datetime64 to get a broader range, to get dates before 1677 and after 2262. And by specifying the unit of a datetime64, we can take more advantage of encoding a resolution and get more narrow typing. So in looking at why datetimes need units, we're going to first compare the Python datetime with the NumPy datetime64. We're going to look at some performance comparisons between these two, talk about how to convert them, and look at datetimes in Pandas and StaticFrame. So first we need to understand how can we encode datetime as data. There's two basic representations in wide use. First, we can store integers for year, month, date, seconds, etc. I'll call this a partitioned representation. Another approach is to store an offset from an anchor. And overwhelmingly, the most common anchor is the Unix epoch. This is January 1st, 1970. So the way that these representations work is we store a unit, some sort of unit, maybe seconds or some other unit from the Unix epoch. And I'll call this an offset representation. So when we look at the Python date and datetime types, these are partitioned representations, and we can think of date and datetime as the same kind of thing, but with different units. With date, we have integers for year, month, and day. With datetime, we have integers for year, month, and we keep going all the way down to microseconds. The NumPy datetime64 implementation is something very different. It's an offset representation. So it's going to use values in a signed int64 way, and it's going to interpret those as offsets. And the size of that offset is given by the unit. So NumPy's datetime64 supports 13 offset units from year all the way to attosecond. As I talk about these, it gets kind of confusing. So when I refer to datetime, I'm referring specifically to Python's date and datetime objects, and we import those from the datetime module. When I refer to datetime64, I'm explicitly referring to the NumPy datetime64 either arrays or elements, and we import those from NumPy as NP. So both NumPy and Python support time delta objects in addition to datetime objects. Time deltas, as might be easily expected, are always represented with an offset. With Python, we can have time deltas from week all the way down to microsecond. And in NumPy, we have time deltas available across the full range of all 13 units there. Okay, so next we're going to compare datetime and datetime64 as a way to help us understand their differences. So first we'll look at constructors. When we create a datetime, a Python datetime object, we provide that exact partitioned representation that is the underlying representation of the object. In addition, datetime has broad support for parsing strings and other representations. With NumPy's datetime64, we can provide an offset as an integer and a unit. Alternatively, we can provide a string using a very specific ISO string representation. NumPy's datetime64 does not support as wide a range of string representations as Python's datetime, and we can create both datetime64 arrays and elements. We'll see examples of these. So when we create a Python date object, as many of us are familiar, we provide each of the partitioned values, the year, the month, and the day. We can also use alternative constructors to provide values as strings or to provide our own parsers. And this is a huge power of the Python date and datetime functions, is that we can parse arbitrary string representations of dates. We can also produce a date from an offset to the epoch, which, as I've already mentioned, is how NumPy's datetime64 representation works. Looking at NumPy datetime64, we can create a datetime64 by giving an offset and a unit, and that's exactly what we're doing here. This will give us one offset of unit size date after the epoch, which, as you might expect, is January 2nd, 1970. We can also provide an ISO string representation of dates and date times, and NumPy is able to parse those and give us the appropriate object back. Now we can do the same thing when we want to create an array. Here I give a tuple of string dates, and I tell NumPy to just interpret these as datetime64. Here I'm not giving a unit, but NumPy properly identifies these as date units. Alternatively, I can even give a tuple of integers and a unit, and NumPy will figure out these are day offsets from the 1970 January 1st epoch. So moving on, we can consider the resolution of each of these types. So with datetime and Python's date object, we have each type offers only one unit. The data resolution may not be the same as the unit, and I'll give you an example of what that means. With datetime64, we have one type that supports all 13 units from year to attosecond. And the data resolution, because we have more types, can actually be the same as the unit. And I think that's an important consideration. So when we create a Python date object and we look at the resolution, we see that it tells us the resolution is 1 day. But here I create a date time, and I've only provided data up to the level of minute. And I look at the resolution, and the resolution is microseconds. The resolution is always interpreted as the minimum unit of the datetime type. Now, with NumPy's datetime64, we can do more. We can specify datetime64 across a wide range of units, and that unit is encoded in the D type. Here we see a year and a month D type. They encode the unit, and we have much more granularity of our units so that the resolution of our data can actually be reflected in the unit of the D type. Okay, what about the range? So the datetime and date objects arbitrarily set their range from year 1 to year 9999. Now, I say this is arbitrary because Python's integers can support a much broader range than this. This is a hard-coded constraint in the implementation of these types. With datetime 64, the range is controlled by the unit we desire and the underlying type, which is an int64. Smaller units thus have smaller ranges. So if we look at a Python datetime object, we see the max and the min is from year 9999 to year 1 for both datetimes and dates. With datetime 64, we have a lot of different ranges available to us depending on our unit. So if we quickly get the minimum and maximum integer on a signed int64, we can use those values to show us with different units what our maximum value will be. So if we create a datetime 64 with the maximum integer and say the unit is a date, we can see we get this astronomical year far, far into the future. If we use that same max int64 integer and we convert it to microseconds, we get similarly, well, not as similar, but also a very large year. If we interpret the same value as nanoseconds, now we get a year that we should recognize, 2262 April 11. In NumPy's documentation, they provide a nice table of all of the ranges of these units going all the way from year to attosecond. And as expected, as the unit gets smaller, the time span gets smaller as well. Okay, what about converting between these units? Well, with datetime, we can create a new object by using a method or a constructor. With datetime 64, we want to use the asType method, and that'll allow us to go between any unit we need. So if we have a date object and we want to convert it to datetime, we simply need to unpack the partitioned values. If we have a datetime object and we want to go to date, we can simply use the date method. For datetime 64, we have a huge range of flexibility simply by using asType. Here I have a datetime 64 of minutes. I simply want to asType this to months. I just provide a datetime 64 representation with the appropriate unit, and NumPy handles the conversion for me as needed. Now, what about shifting? Well, with a datetime, we can only use time delta objects to shift. And using non-day unit time deltas with date objects truncates that information. I'll show you exactly what I mean by that. With datetime 64, we can use operator overloading to add and subtract units with integers, which is pretty convenient. And we can use any time delta 64 with any datetime 64 and implicitly get the right and appropriate unit without losing information. So if we look at shifting a datetime object, we cannot shift a date with an integer. We have to use a time delta. If we have a date object, a Python date object, and we shift it by a time delta that has a microseconds, notice those microseconds are ignored. That's quite different than what NumPy will do with a similar move. If we apply that time delta to a date time, then those microseconds are observed as expected. If we shift to datetime 64, well, here we can actually shift by an integer. We can shift by an integer because the unit tells us what that integer means. And here, that integer is interpreted as a single day. We shift January 2nd to January 3rd. If I have a nanosecond level array and I shift it by 20, well, that's going to shift each date by 20 nanoseconds. And notice that the type of the array has changed to be a nanosecond representation. And that's the same thing I show here, where I have dates and I combine them with nanoseconds, we get a nanosecond array. What about missing time? Well, the datetime and date objects do not offer specialized objects for missing time. We just would use none to serve as a placeholder. Whereas with datetime 64, we have NAT, not a time, which is a nan-like value that can live in datetime 64 arrays. So those NAT values come from nuns or empty strings in the creation of a datetime 64 array. So here I create an array, I say I want datetime 64 dates, and I provide none as my value. This is going to get converted to an NAT. The same thing happens if I provide an empty string. And NATs propagate just like NANs under transformation. So if I have an array with an NAT and I perform a time delta on it, that is going to propagate the NAT in the expected position. Okay, what about the performance of these different types of representations? So you might think, why can't we just put datetime objects in object arrays? Well, object arrays, in order for datetime objects to live in object arrays, NumPy is going to have to unbox each of those objects and perform operations on them. That's going to be considerably slower than what we can do with contiguous data. When we have datetime 64 arrays, what we have are C arrays with contiguous bytes, and that's always going to give us much better performance. So I'm going to do some performance comparisons. You can find these in the StaticFrame repository if you want to look at these or run them yourself. We're going to experiment with about 11,000 dates, and I've created two arrays, a datetime 64 array and an object array of datetime objects. And if we look at the performance of these guys, we see that datetime 64 is always going to be faster. So if we want to find the year of our array of datetime objects, we can just look at the year attribute and put that in a list comprehension. If we compare that to doing an as type operation, the datetime 64 is going to be about 6 times faster. If we want to find all of the dates that are Mondays and produce a Boolean array, we can do that with Python date objects by simply calling the weekday method and comparing it to 0. We can do the same thing with the datetime 64 by transforming the integers such that 0 is Monday and doing the comparison at the level of a NumPy array. And this is going to be about 9 times faster than working with the Python objects. Another common move is we need to do a comparison. We need to split an array of dates into 2 groups. If we do that move with datetime objects, we can do something like this. With a datetime 64 array, we can use this move, and that's going to be about 11 times faster. Finally, if we want to shift the days in an array, to do this with date objects, we would need to create a time delta object and shift each date one at a time. The similar move using a datetime 64 array, we simply need to add 1 and we get exactly what we need. And that is going to be 60 times faster. So there we really see the benefit of using contiguous data in a proper datetime 64 array. So what about converting between these two types? What about going from datetime 64 to datetime and vice versa? Well, moving from datetime 64 to datetime, there might be some challenges because datetime 64 has a more broad range and we're moving to a more narrow range. So some units will result in distorted or transformed values. The way to do this is to simply use the toList method or convert the array to an object array. Now, day through microsecond units convert naturally to date and datetime objects correctly, but units of year and month convert to date, and smaller than microsecond units convert to offset integers. Both of those may not be what you expect. So here we have a NumPy array of datetime 64 days, and we're going to as type these to object, and we see that NumPy nicely gives us back date objects, and nothing is lost. We can do the same thing by going to list. But if we have datetime 64 months and we convert those to objects, we're actually going to get date objects. We're going to introduce a day here that we didn't have before. And the same thing happens with years. So that's something to watch out for. If we want to try to convert a nanosecond or anything lower than microsecond to object, we're going to see that NumPy is going to give us back integers. These are the raw offsets. And this is likely to be an undesirable situation. Going from datetime to datetime 64 is quite straightforward. Here, all we need to do is take our values and as type them to the appropriate datetime 64 representation. Okay, so what we often do with our datetimes is we're using them to label data, and we can do this in Pandas and we can do this in StaticFrame. And Pandas and StaticFrame take very different approaches here. So Pandas provides one datetime index type, the datetime index, and it forces all datetime 64s to become nanoseconds, regardless of what you ask for. StaticFrame has one index type per datetime 64 unit, and we can use datetime 64 units to explicitly specify our resolution and our type. So in Pandas, every datetime 64 is a nanosecond. Pandas stores all values as nanosecond datetime 64 arrays. You don't have a choice. Any datetime 64 array given as an index or given as values is converted to nanoseconds without asking you. We also have this PD timestamp object, which allows a nanosecond resolution in the object domain. So why use nanoseconds everywhere? Few of us use data at the nanosecond resolution, and using nanosecond resolution compromises the range of more common units like dates. And using nanosecond resolution forces the creation of this pd.timestamp object. And again, we have an option to align with Python's microsecond unit in its own datetime, but that option was not taken. So let me show you an example of this. So if we create a series here with a datetime index, and here I'm specifically giving date objects. I'm saying the resolution of my data is at the level of date. We can create a series this way, and things look fine when we just look at the series. But if we look at the underlying array in the index, we can see that it's been converted to nanoseconds. And if we
reminder, you have about 2 minutes left.
Okay, thank you. And if we convert this to object, we see we get a timestamp object. We can as type this at the level of the array, and we get the expected integer offsets. And it doesn't matter how we put the nanosecond array in the Pandas container. If we put the array in as a raw index, Pandas is going to convert it to a nanosecond for us. If we put it in as the actual values, Pandas is also going to convert it to a nanosecond. With StaticFrame, we've taken a very different approach. We have an index type per unit. So we have a family of index types. This encourages the specification of a resolution. It allows us to take full advantage of the available range, and we don't have a need for PD timestamp. So StaticFrame offers this full family of index types, one per unit. And when we create containers, when we create labels, we can specify the intended resolution. So if I have some monthly data, I can create an index year month. And that information, that resolution is retained. And we can see under the hood, we have a datetime 64 month array backing this data. If I want to represent the dates of the Magna Carta or when Martin Luther posted his 95 Theses, I can do that, and I can create an index date object with dates in 1215 and 1517. This cannot be represented in Pandas. If I try to create a series with these values, Pandas will complain that they are out of bounds. And again, that is because Pandas has chosen to represent everything as a nanosecond. So to summarize, in attempting to simplify the datetime 64 by only using nanosecond units, Pandas creates a more complexity by introducing this weird timestamp object, limits the usable range for common use cases like dates, and is forced to do unit transformations behind your back. I'm not the only one to have been confused by this. This Stack Overflow post from about 8 years ago asks about how to convert amongst these various types. Wes McKinney, the original creator of Pandas, answers, "Welcome to hell," clearly expressing frustration with the complexity that exists in Pandas' handling of datetime 64. So in summary, use datetime 64 units, and in doing so, you can do a lot more in encoding your resolution. So you get unambiguous resolution specification. We can know whether we have a monthly time series or something else. We can take advantage of larger ranges. Not everything is a nanosecond, and we can use dates before 1677 and after 2262. And we permit more narrow typing, and I believe more narrow typing gives more maintainable code. The unit becomes part of the dtype. We can make explicit our intended resolution, and we avoid doing any behind-the-back degradation of information. So I encourage you all to explore datetime 64. We should use datetime 64 over object arrays of datetime. I've shown that's always going to be faster. We can use datetime 64 units to express resolutions. Everything is not a nanosecond, nor should it be. And finally, StaticFrame's datetime index family might make your code more maintainable by giving you explicit definition of the resolution of your data. Thank you.